Hi, I'm Junhan Kong from the University of Washington, and with my collaborators Mingyuan Zhong, James Fogarty, and Jacob Wobrock, we present our work, Quantifying Touch, New Metrics for Characterizing What Happens During a Touch. Current performance measures for touch-based systems usually focus on overall performance, such as touch accuracy and target acquisition speed. However, they do not provide information on what happens during a touch and why accuracy and speed are what they are. To understand what happens during a touch, we propose 15 target agnostic metrics that consider the touch process as a time series of ovals from finger down to finger up. For each of the touch ovals in the sequence, we consider its location of touch, the lengths of its major and minor axes, the angle of the major axis relative to positive x direction, which is straight right on the screen, as well as its contact area and timestamp. Based on these properties of touch ovals, we propose 15 touch metrics under 3 different categories: touch direction, variability, drift, duration, and extent based on the location and time of touch, absolute area change, area variability, area deviation, and area extent based on the touch area information, as well as absolute angle change, angle variability, angle deviation, and angle extent based on the touch angle information. We provide mathematical formula as well as intuitive descriptions for each of the metrics we propose. Although our metrics assume that a single finger is performing the touch, multiple concurrent fingers might inadvertently appear on the screen, especially for people with limited fine motor function. Therefore, we discuss 3 policies for handling multiple concurrent fingers. The first down policy calculates our metrics based on the first finger to land on the screen. The longest lived policy calculates our metrics based on the finger that persists on the screen the longest, and the sum of all policy includes all touch traces in the calculation. To evaluate our metrics, we developed a testbed to collect touch data that includes complete touch oval information. We ran studies with 27 participants, including 15 participants with self-reported limited fine motor function and 12 without. During the studies, participants first set up their comfortable area of reach by tapping at the 4 farthest corners they can reach without difficulty. Then participants complete 10 practice trials of target pointing, followed by 10 blocks of 20 trials, which is 200 trials in total, by tapping at the crosshairs randomly generated within this area on the testbed. Using this data, we ran 2 parts of data analysis with our metrics. For the first part, we looked into how the metrics vary between different impairment levels, none, moderate, and severe. For the second part, we analyzed how the metrics are affected by different specific fine motor challenges self-reported by the participants, such as tremor, spasm, etc. We applied mid-ranks to our 15 touch metrics and then conducted analyses of variance using linear mixed models. We ran separate analyses treating the impairment level and then each specific fine motor challenge as a fixed effect and participant as a random effect. We calculated all our touch metrics using the 3 touch policies, first down, longest lived, and sum of all, and found that the analysis results from all 3 touch policies generally agreed, with the sum of all policy magnifying the differences. Therefore, we proceed with presenting our analysis results using the sum of all policy. We found that 6 of our metrics exhibited significant or marginal differences between the non, moderate, and severe groups, which is variability, drift, duration, extent, absolute area change, and area change. Specifically, the severe group experienced much larger values in these metrics compared to the non-group. We also found that a number of the specific fine motor challenges are each associated with a subset of our metrics. Overall, our metrics can effectively characterize different user behaviors and abilities. Moreover, our metrics are target agnostic, making them easy to implement in real-world systems because they do not require any information regarding the targets to touch. Our metrics can be applied in a variety of different areas, such as evaluating the accessibility of different touchscreen devices, helping with the design of touch-based systems that can understand and adapt to users' abilities, as well as diagnosis or tracking of human motor functioning. Thank you for watching. For more details, please refer to our paper, and please feel free to reach out if you have any questions.